So, you may be familiar with pulley arrangements such as this. And the cool thing about pulley arrangements is that you can grab right here on this rope, tug down, and doing this, you are actually, kind of through the pulley arrangement, you're actually able to lift very, very heavy objects. I mean, you can lift a piano. It almost doesn't even make sense. And the reason why this is that, in a sense, we have this piano here, and you have 3 rope tensions on it. So you're like tripling your force. Now, of course, this isn't some magic here. There's got to be some sort of consequence, some con. I mean, you can't automatically just link up some pulleys and lift like the world. So, the drawback of what's happening is that if you take this rope and maybe you manage to tug it down 5 meters, this piano is only going to go up a little bit, maybe 1 meter. That's the drawback. That's how we still have conservation of energy. I mean, this isn't magic. So, I pull down 5, and as a result, the piano rises up 1. So you can say that the motion of my hand and this piano depend on each other. This is the dependent motion of 2 objects. And we call it the absolute dependent motion because we are measuring the position, the velocity, and the acceleration of my hand and the piano here from a fixed point. Maybe a line right here. So that's what absolute means. We're measuring things from a fixed point, a fixed origin, just like we're used to. But actually in the next section, we're going to do relative motion. So I might be here, I might be person A traveling this way. There might be a person B traveling this way. So a relative quantity might be the velocity of B relative to A. That is, if this was me, from my perspective, how fast does it seem like B is traveling? So this is generally known as relative motion. So just a sneak peek into the next section. So in my little test example, I said this rope moved down 5, and as a result, the piano moved up 1. That was just a test, but in this section, we're going to develop the math equations that actually relate the position of my hand to the position of the piano, and the velocity of my hand to the velocity of the piano. And the same for the acceleration too. So that's really the point of this section, to make these equations that describe how the motion of these 2 particles depend on each other. And this concept, in my opinion, is best explained just by jumping into it and doing an example, and you'll see how this plays out, and we'll do a couple of examples to smooth it out, and hopefully you guys get it. We need to determine the speed of this block if we know that we're pulling down this rope point with the speed of 3 meters per second. And our first step is to create variables that measure out the various moving components of the system. So, we only have 2 things here that are moving. One is this point right here, and another is the block that I'm concerned about. You may be wondering, wait, isn't this another thing too? Well, this thing and this thing are both tied together with this rope. Because they're tied together, they move together too, almost as a single object. So really, I treat them as one component. So, I need to create some variables that help me measure position. Okay, so I'll make one variable that measures out the position to point A, where I hold the rope, and I'll call this position variable A. And I'll make another position variable that measures out to the position of my block in question, and I'll call that position variable D. And you may be wondering, wait a second, why are you measuring, it seems like you're measuring the positions from this starting line here. Well, why didn't you pick this? You'll see. There's a reason for that. But just make sure you're measuring these position variables from an origin that's not moving. This is that absolute term right here. Absolute means measuring something based on an origin that's not moving. And as we get into more complicated problems, you'll really see the importance of this statement. So again, I'm going to measure my position variables from this line right here. This line is not moving. This line is really a line in between the centers of my two pulleys, B and C. And this is commonly referred to as a datum, which is a fancy word for origin. So this is my step 1 here. So my step 2, write an equation for the length of the ropes. In this case, there's only really one rope here, but in other problems there could be more. So write an equation for the length of the rope based on the variables you defined. So, again, we have really one single rope here that we're using in this pulley system. This rope has some length L. Let's write an equation for its length. So, tracking my rope starting from A, I'm going to have this length SA. Now remember, SA is a variable. I'm going to be pulling this point down, so that point's going to be going down, and this length of rope is going to be increasing. So it's very important that you just remember that this SA here is a variable. It will change with time. It will either increase or decrease. In this case, it's increasing because I'm pulling that rope down. So for starters, my length, I have my SA. Now at the top here, we'll have a little bit of rope here. Now here's the thing. Again, I can imagine me pulling that rope down. And what this will do is it will pull this thing up, which in effect will shorten the lengths of these cords right here. But this red length right here won't change regardless of what goes up, what goes down. So this right here is a constant. I'll just call it C1, that red line. Alright, moving on. Now, all the rope pieces I have left are these three right here and these two red constants. These three purple rope lengths here are important. The way I can write these is SD, my variable here, minus this constant red length right here. So SD minus that red constant, which I'll just call constant 2. Note that really just gets me one of these right here, but there are three of them. So I've got to times this by 3. So this unit right here, this takes into account 1, 2, 3. So I got my green, I got my first constant here, I got my 3 purples here. Well, really the only other two things I have are this constant right here, which I'll call C3, and this last constant right here, which I'll call C4. So this equation right here gives me the complete length of this rope, L, the length. And just to make things a little simpler, I'll distribute this 3 in here. And now what I'll do is I'll take the derivative with respect to time of each one of these quantities. And remember, I can do that. I can do anything I want to any equation as long as I do it to each side of the equation. So I'm going to take the derivative of the left-hand side of the equation and of the whole right-hand side of the equation, which implies that I do it to each term on the right-hand side of the equation. And the reason why I'm taking the derivative with respect to time is, if I take the derivative of a position with respect to time, what's going to come out? Velocity. The velocity of my rope point A right there. So that's why I'm doing this. So if I take the derivative of respect to time of this L right here, well, L is the length of the rope. Regardless of whether I pull up or down, this length of rope will never change. It's just a rope. You know, it's not going to stretch or contract. So the derivative here is going to be a 0. The derivative with respect to time here, well, that's really going to be the velocity of A. I'll just call this A dot or SA dot. But really it's this velocity of A right here. Derivative of this first C, which is this one right here, again, it's a constant. No matter if I go up or down, there will always be a little arc of rope right there. Therefore, this quantity, C1, does not change with time. That'll be a 0, and I won't even write it down here. Derivative of this guy. SD is a variable. It measures out the position of block D. Therefore, the derivative of the position variable of D will give me the velocity of D, which I'll just say as SD dot. And I can't forget this 3. Remember, this 3 is getting multiplied into this variable. That's why it sticks around. Derivative of this whole thing is a constant. It'll be 0. Derivative of this is a constant. It'll be 0. And of C4, again, it's another one of our, I can't remember which one it was, but it was another one of our red rope constants. Therefore, its derivative is going to be 0. So, this is it. This is the relationship, the dependency of the speed of A on the speed of D. They tell us the velocity of A is 3. Now we have to be a bit careful here. Make sure we're interpreting this symbol correctly. The change of that number SA, that variable SA, with time. We know that A is going down. We start with that. It's going down like this. Well, doesn't that mean that this position variable SA is getting bigger with time then? So the change in that number SA will be a positive. It's increasing. So therefore, when I plug in a number here, it's going to be a positive 3. Be very careful and make sure you go through this argument every time you're plugging in numbers into these rates here. You want to make sure you get the sign correct. So this right here is going to be a plus 3. So 0 equals plus 3 times the velocity of D. And if I just do that math and solve for that SD dot, I'll get that it is a negative 1. Negative 1 meters per second. And that negative should make sense. Here is my block D. We kind of intuitively know that if we drag A down, D will go up. Well, if D goes up, that position length, SD, will be decreasing. Which means the change in that variable, SD, with time, will be a negative. This delta SD is negative because SD is getting smaller and smaller. That change is negative. So, yeah, we definitely should be getting this negative here. So, that's how you do it. And this kind of matches our intuition based on what we talked about at the very beginning. I can lift this big piano thing down here because of this nice pulley system. But this piano won't be moving up as fast as I'm tugging that green rope down. So it sort of matches our common sense here. The pulley system boosts my force but it decreases the distance and the speed that my target object travels. So my last step, step 3, is the whole taking the time derivative part. And I'll write that down now. Yeah, so we took the time derivative of each term in our equation, and from that we got the velocities of the various components, the various moving components in our system for which we had those variables. Of course, we want to be very careful when we plug in the numbers, their speeds. Get the signs right. Make sure you're visualizing how these variables, these lengths, are moving. Are they increasing or are they decreasing? Alright, so we'll do another example here. So we have a rope down here who's drawn towards the motor this way at a speed given by this equation, and we need to determine the speed of cylinder A when t is equal to 1. Well, we basically just plug 1 into this equation. T is 1. 1 to the 1.5 power is just 1. 1 times 5 is 1. So really, this just means that, let's just say this point on the rope is moving this way with a speed of 5. And we need to determine the speed of the cylinder A. And I'm pretty sure it's going to be going up. So we'll kick it off with creating variables that measure out the various moving components of the system. Well, I chose this problem because it's kind of weird. We got ropes going this way, but then we got this. Well, don't worry about it. Just make variables and make sure these variables are measured off of origins that are not moving. Not all of my different variables have to be measured from the same origin. So I'll make a position variable, I'll just call it SM for motor. So here's SM, and it measures out this green point here. So I envision this system moving. This point moves this way. My guy goes up here. So really, my only other moving component here is going to be my cylinder. So this will be SA. And again, this pulley guy right here is really tied with my cylinder by this constant sort of rope length, so it really is all moving together as one component. So I only have one variable here. And again, I'm choosing my origin to be really this line here that's linking the centers of these two pulleys. And because it's a line, we just call it a datum for whatever reason. Alright, step 1 done. Moving on to step 2, let's write our rope equation. Looks like, again, this is all just one rope here. In the next example, we'll see 2 ropes at play. So we still just have one rope whose length will equal, we'll start out with this length right here. That's going to be our SM variable. So we got that. This next section here, this is just going to be a constant. Regardless of whether we move up or down or left or right, there's always going to be this red rope filling this space. So this is going to be constant, C1. Now, from here, what draws my attention are these 3 rope lengths here. And I'm treating these together as one sort of thing. They really pop out to me because they're really measuring out, they're lengthening or decreasing depending on how that purple system moves. So because of that, I know they're going to be in terms of my position variable A. So the way I can get these 3 ropes here is going to be my SA minus this distance right here. And again, this distance, that red distance, is just that constant cable linking my cylinder to the center of that pulley. So it's going to be SA minus a constant C2, which will be one of these purple ropes. Of course, I have to multiply this by 3 to get all 3 of them. Now, here's a tip that I always apply. I'm totally fine proceeding with this, like we did in the last example. We did a thing very similar to this, where we subtracted off this constant rope. But what I always do, instead of making a variable all the way out to that cylinder, I'm just going to make a variable only to my pulley and call this SA. Now, obviously, this position variable A is not measuring out the position truly to my cylinder A. But I know I'm going to take the derivative. I'm going to set up my equation, take the derivative, and I know I'm going to get SA dot, which of course is going to be the velocity of my pulley. But remember, this pulley here is linked statically with this cylinder here. They're both tied together, which means they're both going to have the exact same velocity and acceleration, but obviously not the same position. That's okay, because I'm only really concerned about velocity. And in later problems you'll see that we care about acceleration too. So since the velocity and acceleration of these two things are the same, I'm totally fine just making my SA variable measure out to this pulley here, just so I can save time and not have to go through writing out that constant between them. So actually, let me switch gears just so you guys can see it, because I do this all the time, and as you guys get better at doing all this stuff, I'm sure you'll do it too. I'm going to make this SA variable measure out to the center of my pulley. So I'm going to erase this work here. I got my green down there. I got my first red constant. Really, I just have 3 of these SA lengths, because remember, I'm measuring out my pulley now. If this pulley travels downwards, those 3 rope lengths are going to increase too. So I have 3 of those purple rope lengths. I have a constant right here, which will be SC3, and 1 more rope constant that'll always be there, C4. So now I'll take the time derivative of each term. This number L, the length of the rope, won't change with time. It'll be a 0. My variable SM will be changing. It actually will be increasing if my motor is tugging that rope to the right. And the derivative of this constant length here, of course, will be 0. It won't be changing with time. Derivative of this is going to be 3 times the velocity of that pulley. And of course, the derivatives of these two things are going to be 0, because these are constants and they don't change with time. So my equation that I'm getting here is really this. Alright, time to put in the numbers. They tell me that this rope point is moving 5 to the right. I know that that means that this point is going to the right like this, which means my SM variable is going to be increasing with time, which means this is going to be a plus 5. And with that, we can solve for the velocity of my pulley right here. And doing that math, we'll get a negative 1.67. So remember, SA dot is the rate of change, the instantaneous rate of change with my variable SA with time. We're getting a negative, which means my SA number, that SA length, is decreasing, which in turn means that this thing must be going up. That's what it implies. And finally, just to finish things off, this is the speed of this pulley here. But of course, I remember my argument that this pulley and my cylinder move together perfectly. They're tied together, they have the same velocity and the same acceleration. So therefore, this 1.67 is also the velocity of my cylinder. That cylinder A is also moving upwards with a speed of 1.67. Alright, hope things are making sense. We'll do one more. Alright, so a more complicated looking one here. We're told that our block A here is moving downwards with a speed of 4, and we want to know, as a result of this, how quickly is our block B going to be moving up. The trick here is we actually have two different chords here. Here's a red one, and here is a blue one. That just means we're going to do two chord equations. It's a little bit of a curveball, but not too much. You'll see. So, let's identify the moving components of this system. And then let's make some position variables that measure their positions. So, here's a block A. So I need a variable that measures its position, and just make sure that this variable is based off of an origin that's not moving. Don't make the mistake and measure this block out from this pulley right here, because this pulley, if you imagine this system moving, this pulley is going to be moving. It is this pulley right here that's really fixed into the wall. So I want my position to be measured out from there. So there's SA. Now I see that this pulley right here, that's going to move somehow in some way. So I also want to measure it from that same point 2. We have an A, we have a B, I'll just call this SC. And it measures out this pulley right here. And lastly, here's this pulley. Now I know that this pulley and this block here, they're connected via that rope. They're going to move together with the same velocity and acceleration. So as we discussed last time, let's simplify it a bit, and let me just make a position variable that measures out that pulley, and I'll call that SB. So again, we'll find the velocity of this pulley, but we know that the velocity of the pulley and the velocity of this block are going to be the same. Okay, so let me call this first rope right here rope 1, and let's start crafting that rope length equation. So my rope 1, let's start out with this length right here. That'll be an SA. Next, I'll have a little bit of constant. I'm not even going to write it. I know when we take the derivative of it, it comes out to being a 0, so really, I'm not going to write it. From there, I'm going to have these two yellow lengths. I hope you can kind of see that. Let me zoom in. We're going to have two of these yellow lengths right here that measure out the position of this moving pulley. Let me just make sure I make our datum here, that origin for all of our position variables. I'm not going to write it. So I'm going to have two of these yellow rope lengths, SC, and of course they're going to be variables because this thing may be moving down, which means those yellow lengths are going to be increasing to let that pulley lower down. Alright, got a little bit of rope constant right there. That's always going to be there. Not going to write it. And one last rope constant right there. That's just always going to be there. Not going to write that. So, got my length. of my rope 1. Now I have my second rope right here. So this will be rope 2. And I'll start up by saying, alright, I'm going to have a purple length right here. Got to be careful. This is only going to be 1 SB. Don't fall into the habit that, oh, we have a pulley, so we're going to have 2 of them. No. We have this little bit right here as well. Now, what this is going to be, this is actually going to be the difference in between my purple pulley and my yellow pulley. If my yellow pulley is here, I'm going to have a SC like this, and I'm going to have an SB like this, and therefore this rope length here is going to be SB, the purple, minus SC, the yellow. So this, I feel bad because I wish this picture was bigger, but this little bit of brown rope length right here, that's going to be the difference in between the purple variable and the yellow variable. The difference in between the position of the purple pulley and the yellow pulley. And we're going to have 1 of these. And of course we have a couple of constants here and here to finish out that rope length. But again, I won't write them. So if I take the derivatives really quickly, let's do the top. The derivative of the rope 1 length, of course, is 0. And we'll have the velocity of rope A plus 2 times the velocity of pulley C. Doing the derivative of each term here, I'll have a 0 is equal to the velocity of my pulley B plus another velocity of my pulley B minus velocity of my pulley C. So really, there's 2 of these, so I'll just write 2 SB dot. Alright, so I got my derivatives. Now it's time to plug our numbers in. We're given that block A is moving downwards with 4. This downwards means that my SA is going to get ever bigger. Therefore, this is going to be plugged in as a positive 4. Well, I can do a quick solve for the speed of my pulley C, and I'll get a negative 2, which means that pulley C is moving upwards at a speed of 2 meters per second. I'll take this negative 2, plug it right in here, and doing that math, we learn that the speed of pulley B is going to be a negative 1 meters per second. And of course, the negative 1 means that this pulley B is moving upwards. And just as a final remark, the speed or the velocity of pulley B is the same as the block in question. So therefore, this is the velocity of block B, 1 meter per second going up. So, you can see how complicated this can get, especially when we start having to add and subtract our variables here to get those different rope lengths to appear so we can craft that rope. So it gets especially hard when you have to do that. So in the next couple of problems, we'll get into some complicated examples, really flex this out. Hope this made sense. Hope you were able to follow everything. If you have any questions, please ask them in the comments.